Hello everyone, welcome back to part 2 of chapter 11 where we're talking about liquid solids and primarily the intermolecular forces between them. And so we're going to continue along with this objective of looking at the differences between the different intermolecular forces. So these intermolecular forces, as I said at the very beginning, have a lot to do with function and structure. They also have to do with how they react with other things. So one of those ways that they react with other molecules is solubility. And solubility is basically, can they dissolve in each other? Will they mix with each other? And so the attractive forces between the solute and solvent molecules are where this is going to come into play. The rule to remember is always that like dissolves like. Okay, and so if you have something that's polar, it's going to dissolve in polar solvents. If it's nonpolar, it will dissolve in nonpolar solvents. So that's why oil, which is nonpolar, and water, which is polar, don't mix. Okay, miscible liquids will always dissolve in each other. So you'll hear a lot of times we'll say soluble in something. We're usually talking about a solid in a liquid, okay, or a gas in a liquid. But miscibility is liquids in liquids, and so that's the only difference between those terms. A lot of molecules are not just polar or nonpolar, but they're long enough and they have different ends, okay? And so they might have a hydrophilic part to the molecule, water loving, or they might have a hydrophobic part in another area of the molecule. And so when we're looking at how things become soluble, we are actually looking at a competition between how strong is the attraction between the molecules of the same type versus the attraction for the molecules that are different. So for example, pentane, and that word you see immiscible there, immiscible is basically that it doesn't mix together. So you would form two distinct layers like you see here in the beaker. So pentane, C5H12, is a non-polar molecule. It's an organic molecule. It doesn't have any O's. It didn't have anything electronegative. Water is a polar molecule, okay, and we've looked at water quite a bit, and if you remember, it's got a polarity slightly negative on the side where all those electrons are on the hydrogen, creating a slightly positive end on the side where the hydrogens are. The attractive forces between water molecules that you're seeing here is a lot stronger than the attractions between the water molecules and the pentane molecules. And the result is that they're not miscible, or they're immiscible, so they don't mix. So you can pour them together, you can shake them up, and they're still going to separate into two distinct layers, because primarily one is polar and one is nonpolar. So they are going to be immiscible in each other. So one of the strongest dipole-dipole interactions we see in chemistry is the hydrogen bond. And hydrogen bonds occur when you have a very electronegative atom like nitrogen, oxygen, or fluorine, and it tends to pull at the hydrogen in another molecule. And because hydrogen really doesn't have other electrons, when it's pulled away, the nucleus then is exposed, if you will. So there's a proton that becomes exposed. And the proton that's exposed on there becomes a concentrated positive charge because it doesn't have anything connected to it. And so it attracts electron clouds from other molecules. So since you're going to see that exposed proton where we kind of write it like that partially positive charge, it's going to be attracting the negative ends of other molecules. And so that gives us this electrostatic attraction. That's the form of a hydrogen bond. Notice it's not a bond, okay? We call it a bond, but it's not. It's an attraction, electrostatic attraction between hydrogen and a very electronegative atom. So when you have hydrogen, when you have a hydrogen bond, you're going to see that partially positive, and it's going to be on that H that's attached to a very electronegative atom. That's why these aren't partially positive, they're just there. They're neutral. The partial positive one is the one that's going to be connected to the oxygen, because the oxygen is very electronegative, pulling the electrons towards it and leaving the hydrogen with that kind of exposed proton side. So those hydrogen bonds are your example of dipole-dipole, right? Because the dipole of one molecule is attracted to the dipole of the other. Another type of attraction is the ion-dipole. And you see this in ionic compounds, okay? And we've seen this where the difference in electronegativity is so great between the halogen here, okay, and oxygen or hydrogen or whatever, that it completely releases electrons or completely takes an electron. This ion dipole, so we saw when we made ionic compounds that we had this transfer. When we've made them, what that does is it gives us a very positively charged or a very negatively charged nucleus that is then going to be attracted to the opposite charges on other molecules, and that's dipole-dipole. Okay, so the strength of the ion-dipole attraction, so how strongly those are attracted to each other, is going to determine if they're going to be soluble or not. So how strong is this interaction right here? If it's really strong, it's going to be soluble in that. And so in the case of chlorine, which is got a minus charge, it's going to be attracted to those positive ends of the water molecule. With the sodium, it's going to be attracted to the negative end of the water molecules, and that's why sodium chloride is water soluble. So a summary of these, I like to give you a summary slide whenever possible. The intermolecular forces we talked about, dispersion forces, everything has these, okay, everybody. They are the weakest of the intermoleculars. They are present in all molecules and atoms, and their magnitude increases with the molar mass. So the bigger you are, molecules-wise, the higher the dispersion forces are going to be, the stronger they're going to be. Polar molecules are going to have dipole-dipole because you're going to have a partially positive and a partially negative end to those polar molecules. Hydrogen bonds are a type of dipole-dipole. It's the strongest intermolecular force that a pure substance can have. And it's present when you have the hydrogen directly bonded to ONF or some other very, very highly electronegative, okay? And finally, ion dipole, we talked about last. It's in ionic compounds when you mix them with polar molecules like water. It is the strongest intermolecular attraction, and you especially see this in aqueous solutions, things that are dissolved in water. And so kind of the same material, but I was giving it to you in a visual table form for those of you who like that. So you have dispersion, dipole-dipole, hydrogen bonding, and ion dipole, what they're present in, and then what they kind of look like drawn out, and then the strength of the bond. So notice dispersions are the least strong all the way up to your ion dipole. So that kind of gives you a visual of the strength of these and how they kind of fit in with putting these molecules together and impacting the solubility of the molecules when they are in a solvent. All right, so that ends our discussion on intermolecular forces.